Hello everyone. So in this one shot, I'm going to cover wave optics. So I'll cover all concept, derivation, and important questions that can be asked in your board exams. So let us see the syllabus first. So first, we'll study the concept of wavefront and what is Huygens principle. With the help of Huygens principle, we can draw wavefront at a later instant. Then we'll also study the proof of law of reflection and law of refraction by using Huygens principle. Then we'll study what are coherent sources and then how we can have a sustained interference pattern in case of a coherent sources. Then the interference, and then we'll study Young's double slit experiment in detail and different terms that are related to Young's double slit experiment, like the position of the bright fringe, dark fringe from the central maxima, and then what is the angular fringe width, what is the fringe width. All those concepts we'll study in Young's double slit experiment. Then we'll study the diffraction and the diffraction due to a single slit, and what is the width of central maxima. Polarization and the resolving power of optical instrument has been deleted this year, so we don't have to study those topics. So according to this theory, if there is a point source, and if you take the locus of points which are equidistant from this point source, now the locus of these point is known as a wavefront, and the different points on this wavefront will act as the secondary sources. So these are secondary sources. Now these secondary sources will generate secondary wavelets, and these secondary wavelets will travel with the speed of the wave, which is nothing but 3 into 10 raised to power 8 meters per second in vacuum. Now let us understand the propagation of energy in the form of wavefronts with an animation. So let us see. So we have a wavefront. Now these are the secondary wavelets which are being generated, and the common tangent to these secondary wavelet give us the new position of the wavefront. So this is all about Huygens wave theory. Now let us see the key points. Whatever I have mentioned here, let us see that in writing. So first, the locus of all points, locus of all the particles vibrating in the same phase is known as a wavefront. Second point, the light travels in the medium in the form of wavefront. Third, every point on the wavefront becomes the source of secondary wavelets, and it emits secondary wavelets in all directions which travel with the speed of light. And the tangent plane to these secondary wavelets represents the new position of the wavefront. So these are the key points about Huygens wave theory, and you have to remember this. Now let us see different types of wavefronts. So there are three types of wavefront. One is spherical, second is cylindrical, and third is planar. Spherical wavefronts are produced by the point sources. Cylindrical wavefronts are produced by the linear sources. And plane wavefront, we can say if we observe spherical wavefront at a large distance, it appears as a plane wavefront. Now let us see. So in case of a point source, we have spherical wavefronts, and the amplitude of wave is inversely proportional to the distance from the source, where r is the distance from the point source. Similarly, intensity is inversely proportional to the square of the distance from the source. In case of a linear, or you can say cylindrical wavefront, amplitude is inversely proportional to the square root of the distance, and the intensity is inversely proportional to the distance from the source. In case of a planar wavefront, intensity and amplitude does not change. So you have to remember these concepts. Now let us see the proof of law of reflection by using Huygens principle. So let us first see this animation. So basically, this is the incident wavefront that you can see. Now when this incident wavefront hits this reflecting surface, then these are the point of, you can say, these are our secondary sources which are producing secondary wavelets, right? And if we draw a tangent plane to these reflecting secondary wavelets, then we will get the reflected wavefront, right? So now let us see the construction for this. So first I'm showing the proof for law of reflection. So this is the reflecting surface, and let us say this is the incident wavefront. This is incident wavefront. And we know that the light rays are perpendicular to the wavefront. So these are the incident rays, we can say, right? So I'm showing two incident rays which are perpendicular to the incident wavefront, and the angle of incidence is I. Okay, let me call this point as A and this point as B. Now, so the ray, so you can say the ray at B, it reaches point B prime in what time? Let us say it takes t time, right? So this distance will be given as speed times the time. So this is the distance, right? So in that time, there will be a secondary wavelet which is being produced, which will be generated at A, and that secondary wavelet will travel with the speed of the wave. So if I draw a radius, a circle of radius Vt, so let me draw that circle. So I'm drawing a circle of radius Vt. So this radius is Vt. Right. So if I draw a tangent from B prime on this circular arc, let us draw that. And I'm calling this point as A prime. So we can say this A prime B prime is the reflected wavefront. Reflected wavefront. Right. So if I draw a ray from A to A prime, similarly, I can draw a ray which is perpendicular to A prime B prime. So these are reflected rays. And we can say this angle will be the angle of reflection. Right? Let us see. Let me show some important angles. So if this angle is I, then we can say the incident wavefront will make the same angle with the horizontal. So this angle will be I. Let me show you. So this angle is I. Similarly, if this angle is R, this angle will be 90 minus R, and this is right angle, right? Right angle triangle. So this will become R. Now, in triangle A, B, B prime, this is 90 degree, right? So we can say sine of I, which will be perpendicular, which is Vt by hypotenuse, which is A prime, A B prime, right? A B prime. And in triangle A prime and B prime, in this triangle, we can say sine R is equals to, again, Vt perpendicular upon hypotenuse, which is A B prime. Now this is the first equation. This is the second equation. By comparing these two equations, we can say sine I is equals to sine R. So from this, it implies that angle of incidence is same as the angle of reflection. So this is nothing but the law of reflection. So we have proved law of reflection by using Huygens principle. Now let us see the proof of law of refraction by using Huygens principle. So before that, let us see the animation of refraction. So this is the incident wavefront, and it is approaching an interface which is separating two media. Now the rays will enter from one medium to another, so the speed of you can say the light will change. Okay, let us see. So these points, so if I show you, these are the secondary sources, right? And these secondary sources will generate secondary wavelets, and which will travel with a new speed because now the medium has changed. So let me again show you. So we can say, if I draw a tangent plane to this, it will be the refracted wavefront. So let me just show you the derivation for that. So we can say this is the incident wavefront, and I'm considering this point as B, this point as A. And this is the normal at the point of incidence. And let us say the ray makes an angle I with the normal. So this is the angle of incidence. If this angle is I, and we know that the ray is always perpendicular to the wavefront, so this angle is also I, and this angle will be 90 degree. Now if I draw a refracted wavefront, so we can say this is the refracted wavefront, right? And I'm calling this point as B prime. And let us say this is the ray, refracted ray, and this point as A prime. So this angle will be 90 degree, and this is the refracted ray, right? So if this angle with the normal is R, then this angle will be 90 minus R. So I can say this angle will be R. Now we have two right angle triangles. So there are two right angle triangles, triangle A, B, B prime, and there is another right angle triangle which is A, A prime, B. And let us say this medium has a refractive index mu1, and this medium has a refractive index mu2. And the speed in this medium is v1, and the speed in this medium is v2. And we know that speed v1 will be given as speed of light in vacuum divided by the refractive index. Similarly, v2 can be written as c divided by refractive index. Okay, so in same time, so let us let us say the ray which is at B takes t time to reach B prime. So what is this distance? Let me take different color for that. Yes. So this distance will be speed in the medium 1 times the time. Similarly, the distance A prime in the same time, this distance will be V2 times t. I hope it is clear. Now, in right angle triangle AB prime, we can say sine I will be equals to perpendicular upon hypotenuse. So perpendicular is BB prime and the hypotenuse is AB prime. So we can say it will be V1t divided by AB prime. Similarly, in right angle triangle A prime B, we can write sine R as perpendicular, which is V2t divided by the hypotenuse, which is AB prime. Now, if we compare this equation 1 and 2, then we can say sine I divided by V1 is equals to sine R divided by V2. And from these two equations, we can write V1 in terms of refractive index. So we can say V1 is, so this will be mu1 sine I divided by C is equals to mu2 sine R divided by C. So C will get cancelled out. And this equation is what? So it is giving us sine of I to ratio of sine of I to sine of R as mu2 by mu1, where mu2 by mu1 is the refractive index of the medium of refraction with respect to the medium of incidence. So I can write this as mu2 1. And this is nothing but the Snell's law. So we have derived Snell's law by using Huygens principle. So that is the proof. Now let us discuss the concept of coherent sources. So let us understand this with an animation. So here we have given two balls, and we are going to oscillate these two balls on the surface of water, and when they oscillate they will produce waves. And there are two another ball which are also on the surface. One is orange, other is purple. Now let us see what will happen. Now both these balls are oscillating with the same angular frequency, so with same frequency. Now if you look at this orange ball is oscillating with an amplitude which is greater than the amplitude of both the sources. But if you look at the purple one is at rest. So what we can say, the orange one is at a location where we have constructive interference, where we can say the crest are aligned with each other. So when we have two waves which are in phase, then we'll have an increase in amplitude. This is known as constructive interference. But if you look at the purple one is not at all moving. Why? Because it is at a location where the crest is aligned with the trough. So here the destructive interference is happening. So in order to have a coherent sources, or in order to have a sustained interference pattern, there are three important conditions. First is both the sources must be having a constant phase difference between them. Like in this particular case, these sources are in phase. So there is no phase difference. So we can say the phase difference is zero. So it means it is a constant phase difference, which is zero. But and the second important condition is they must be having the same frequency. Now both these sources are oscillating with the same frequency. And the third important condition is that they should send waves nearly in the same direction so that the waves can reach at a point simultaneously and interfere. So we should remember these important conditions. Now let me give you the example of two waves produced by two sources. Say y1 is a1 sine kx minus omega t, and let us say y2 is a2 sine kx minus omega t. Right? Now we can say the phase difference is zero. So this is a one type of a case of coherent sources. Let us see the another case where y1 is a1 sine kx minus omega t, y2 is equals to a2 sine kx minus omega t, and let me take some phase difference between them. Let us say pi by 3. Now the phase difference between these two waves will be pi by 3. Again, the phase difference is same, is a constant value, that is pi by 3, and both have the same angular frequency. Similarly in this case. So these are the example of coherent sources. Right. So now let us see what is interference. So I'm going to take two waves, y1 which is a1 sine kx minus omega t, and y2 which is a2 sine kx minus omega t plus phi, where phi is the phase difference between these two waves. Now by the principle of superposition, if we want to find the resultant wave at a particular place where two waves are reaching simultaneously, by the principle of superposition, the resultant wave will be nothing but the vector addition of both these waves. So y1 plus y2. So we can say a1 sine kx minus omega t plus a2 sine kx minus omega t plus phi. Right? So let me show you the case. So we have a source S1, this is the source S2, and the waves from these two sources is reaching at point P simultaneously. Let us say this distance is x and this distance is x plus delta x. So what is the path length difference? We can say it is delta x. So delta x is the path length difference. So this phi is nothing but k delta x. So phi is nothing but k delta x, because we can write x as x plus delta x. So if you write x as x plus delta x, then there will be a k delta x term, and that k delta x term is nothing but phi. So do remember this. And k is nothing but 2 pi by lambda, that you must have studied in waves. So do remember this relation. This is the relation where we have compared path length difference with the wave difference, path length difference with the phase difference. Right. Now when we have harmonic functions, the way to add them is we can use a technique known as a phasor technique. Now the phase difference between them is phi. So if I represent first harmonic function with a rotating phasor, let us say this is a1, and the second wave I can represent with a2, and the angle between these two is phi, because the second wave is leading the first wave by phi. Now both these phases will rotate with the same angular velocity because their angular frequency are same. So if I want to find, so I can write yr as ar sine kx minus omega t plus theta. And now, so here we have to find the value of ar and theta. So ar is nothing but the resultant of a1 and a2. So this is ar, and it makes an angle theta with the phasor a1. So we can say ar, or the resultant wave, is leading the first wave by theta. So I can write ar as root of a1 square plus a2 square plus 2a1 a2 cos phi. And we know that intensity is directly proportional to the square of the amplitude for a given frequency. So I can also write this as IR as I1 plus I2 plus 2 times root I1 I2 cos phi. Now that is the intensity for resultant intensity, and this is the resultant amplitude. And if I want to find this theta, so we can say that is not required as per the exam is concerned, but let me write down the formula. So tan theta is nothing but A2 sin phi upon A1 plus A2 cos phi. So from here we can find the value of theta, right? So if intensities are same, if I1 is equals to I2 is equals to I naught, then resultant intensity can be written as, by using the concept of trigonometry, it can be written as 4 I naught cos square phi by 2, right? Now let us see the case of constructive interference. So in constructive interference, intensity is maximum, right? Intensity is maximum. So if intensity is max, to make the intensity maximum, cos phi has to be 1. So cos phi is equals to 1. So when do we have cos phi 1? It will be at 0, then 2 pi, then 4 pi. So we can say phi should be equals to 2n pi, where n is an integer. And we know that phase difference is nothing but 2 pi by lambda times delta x. So we can find the path length difference from this. So 2 pi by lambda times delta x is equals to 2n pi. Now this 2 pi will get cancelled out. So delta x comes out to be n lambda. So it means to have a constructive interference, the path length difference should be integral multiple of lambda. Now let us see. So in case of a constructive interference, intensity is maximum. So we can say I max will be square of root I1 plus root I2. And we can get this by just substituting cos phi equals to 1 in this formula. Similarly, maximum amplitude will be given as A1 plus A2. Right? So now let us see the case of destructive interference. In destructive interference, the intensity is minimum. So it means to make IR minimum, cos phi has to be minus 1. So to keep cos phi as minus 1, so we know cos phi is minus 1 at pi, 3 pi, 5 pi. So we can say phi should be an odd multiple of pi. And this phi can be written as 2 pi by lambda times delta x. So 2n minus 1 times pi. So this pi will get cancelled out. So delta x comes out to be 2n minus 1 lambda by 2. So we can say for destructive interference, path length difference has to be an has to be an odd multiple of lambda by 2. So in case of destructive, the intensity is minimum. So we can say it is the square of I root I1 minus root I2. And the minimum amplitude will be modulus of A1 minus A2. So these formulas we have to remember, right? Okay, right. So now let us see how we can produce coherent sources by splitting of the wavefront. So here we have a planar wavefront, and if we place a cardboard with two slits, now these are two slits, right? These are two slits. Now when these wavefronts hit this cardboard or these slits, then we have the source of secondary, or you can see we have a source of secondary wavelets, and these secondary wavelets will be spherical in nature. So you can remember this. And we're going to use this concept to study Young's double slit experiment. Right. So let us see what is Young's double slit experiment. So in Young's double slit, we have two slits. Let us say here we have two slits. Now these two slits are acting as two coherent sources. And here we have a screen, right? So here we have a screen. So we're going to study the sustained interference pattern on the screen by these two coherent sources. Let us see what happens. So these two sources are generating spherical wavefronts, Now these spherical wavefronts, they are approaching the screen, right? So when they approach the screen, then we'll see a sustained interference pattern, because there will be a region where constructive interference is happening. For example, at the brightness, we have constructive interference. At the darkness, we have destructive interference. So in Young's double slit experiment, we will see alternate dark and bright fringes. And let me just show you some important fringes. This fringe, which lies at the perpendicular bisector of S1, S2. S1, S2 are the sources, coherent sources. This is known as the central maxima, right? So this is the central maxima. This is the first maxima. This is the second maxima. This is the first maxima below the central maxima. This is the second maxima. And if I show the minimas, this one is the first minima. This is the second minima. This is the third minima. Similarly, this is the first minima below the central maxima. This is the second minima, and this is the third minima. We're going to discuss these in more detail. Let us see the derivation for that. And in this derivation, we're going to find the position of the maxima, right? First maxima, second maxima, first minima, second minima. Let us see. So let us, this is the Young's double slit experiment, right? And setup. And here we have the screen, and on the screen we have a sustained interference pattern. So let me show you the screen. So we have a double slit, and let us say planar wavefronts are approaching. So planar wavefronts are approaching the double slit, right? So we have planar wavefront. Now, in order to find the intensity at a particular point on the screen, what we can do, we can draw two rays from the sources. So there is a ray S1P and there is another ray which is S2P, right? These are the two rays. So in order to find the intensity at a point on the screen, we should know what is the path length difference. So here, the path length difference will be given as S2P minus S1P, right? And let me just mention some important distances. Now, the distance between the slits and the screen is known as capital D, and the distance between the slits is small d. So we should use this nomenclature in YDSE. It is also known as YDSE, right? Young's double slit experiment. So we want to find delta x. So here we're going to use some assumptions. So let us see the first assumption. If capital D is very large in comparison to small d, right? Let me show you. If this is S1 and this is S2, and if P is quite far from S1 and S2, and if I draw the rays from S1, S2 up to P, then these rays will look nearly parallel to each other, right? So we can assume rays are parallel to each other. This is S1, this is S2, and both these rays are going towards P, right? It is going towards P. Now to find the path length difference of two parallel rays, what we can do, I can draw the perpendicular from S1 over S. This is 90, and the distance between the sources is given as D. So what I can say, if so the position of P from the perpendicular bisector is theta, so we can say this angle is theta, this angle is also theta, this angle is theta. So it means this S1M will make an angle theta with S1, S2. Now in this right angle triangle, the path length difference is nothing but S2M. So that is the path length difference delta x. So delta x can be written as d sine theta by using trigonometry. So we should remember, if this assumption is valid, if capital D is very large in comparison to small d, and usually d is 1 meter and small d is 1 millimeter in most of the questions. So if this is valid, then we can write delta x as d sine theta. Now let us see the second assumption. Second assumption is this position of P from this point O is Y if Y is very small in comparison to D. Or we can say if you have given lambda to be very small in comparison to D, then the second assumption is valid. If Y is very small in comparison to D, we can say theta is small. If theta is small, we can write sine theta nearly equal to tan theta. So sine theta can be written as tan theta, and delta x can be written as d tan theta, because d sine theta we just calculated it is when the first assumption is valid. So when both the assumptions are valid, delta x will be d tan theta. And what is tan theta by using trigonometry? It will be y perpendicular upon base. So this can be written as dy by capital D. So this is the path length difference. Now we can find the position of different maximas, right? Basically, we have to find the value of y for different maximas or minimas. Let us see. Position of bright fringes. So these are known as fringes, right? These are bright fringes, and we want to find the position of bright fringes. So what we can say, at bright fringes, we have constructive interference. So this is the central maxima, right? This is the central bright fringe. And we can say delta x should be equals to n lambda that we have just studied in interference. So d y by capital D should be equals to n lambda, or we can say y should be equals to n d lambda by small d, where n can be 0, 1, 2, 3, right? So on and so forth. So if you put n equals to 1, so y will be d lambda by small d, and if you put n equals to 0, we'll get 0. So it means at this, these are the sources S1, S2. So this is at this the delta x is 0, right? Delta x is 0, and it is known as central maxima or 0th order maxima. Similarly, at this is the first maxima. At this, the delta x will be lambda. So if delta x is lambda, then y will be d lambda by small d, right? That just we have calculated. And at this, and this is basically the first maxima, or you can say first order maxima. At the second maxima, delta x will be 2 lambda, and this is known as second maxima or second order maxima. Similarly, below the central maxima, delta x will be minus lambda, and we can say this is the first maxima. And this is the second maxima, where delta x will be minus 2 lambda. Similarly, we can show the position of minimas. So let us see. So position of dark fringes. So in case of dark fringes, we have destructive interference. So delta x should be equals to 2n minus 1 lambda by 2, odd multiple of lambda by 2, and this can be written as y can be written as 2n minus 1 d lambda by 2d, d lambda by 2d. So if I substitute n equals to 1, y will be d lambda by 2d. If we substitute n equals to 2, then y will be 3 d lambda by 2d. Okay, let me show you. So this at this, the delta x is 0.5 lambda, and this is the first minima, and its position is d lambda by 2d. Similarly, at this, delta x is minus 0.5 lambda. Again, it is first minima, and its position from the central maxima will be d lambda by 2d. Similarly, this is the second minima, and here the delta x will be minus 1.5 lambda, and its position from the central maxima will be 3d lambda by 2d. Similarly, this is the second minima, where delta x is 1.5 lambda. Again, its distance from central maxima is 3d lambda by 2d. So I hope the position is clear to you. Now there is one more important term that we used to study is the fringe width. Let us say fringe width. So fringe width is the distance between two successive maximas or two successive minimas on the screen. So if you look at the distance between two successive maxima, it comes out to be d lambda by d. So it is denoted with beta. So it will be d lambda by small d. Then we'll define angular fringe width. And what is angular fringe width? If this is, these are the slits S1, S2. And let us say on the screen, if we consider a length, which length equivalent to beta, but the angle which this length subtends at the center of the two slits, this angle is known as angular fringe width. So theta will be, so if this distance is capital D, so theta will be beta by capital D. So it comes out to be lambda by D. So lambda by D is the angular fringe width. Now let us see some illustration. So how does the fringe width of interference fringes changes when the whole apparatus of Young's experiment is kept in liquid of refractive index 1.3. Now the fringe width uh, is given as d lambda by small d. So we can say it is directly proportional to the wavelength. So if we change the medium, the wavelength decreases, right? So it will decrease by the factor 1.3. So if the wavelength is decreasing, then the beta will also decrease by the same factor, right? So that is the answer of this question. Now laser light of wavelength 640 nanometer incident on a pair of slits produces an interference pattern in which the bright fringe are separated by 7.2 millimeters. So basically 7.2 is nothing but the fringe width. So d lambda by small d is given as 7.2 millimeter. And lambda is given as 640 nanometer. Calculate the wavelength of another source of light which produces interference fringes separated by 8.1. If this is beta 1, we are using a different source which produces fringe width as 8.1 millimeter. So let us say this is lambda 1, so we have d lambda 2 by small d. Since beta is since the fringe width is directly proportional to the wavelength for a given setup, so we can say lambda 2 by lambda 1 is equals to beta 2 by beta 1. So lambda 2 will be lambda 1, which is 640 times beta 2 is 8.1 divided by 7.2, which is beta 1. So this is 9, this will be 8, and this will give us 80. So it comes out to be 720 nanometer. So lambda 2 should be 720 nanometer. Also find the minimum value of order n of the bright fringes of shorter wavelength which coincide with that of the longer wavelength. Right, so if we use both the lights on the same setup, now we have to locate the distance of the closest maxima where their maxima are coinciding with each other. So let us assume that n1th maxima of lambda 1 is coinciding with n2th maxima of lambda 2. So we can say what is y in case of y is the distance of the bright fringe from the central maxima. So what is y1? So we can say it will be n1 d lambda 1 by small d, and it is same for the second wave. So it will be n2 d lambda 2 upon small d. So from here we can say n1 by n2 will be equals to lambda 2 by lambda 1. Lambda 2 is 720, lambda 1 is 640. So this will be, so we can say it will be 8 by 7, right? Sorry, 8 by 640, right? Sorry. It will be 9 by 8. Now we know our, the ratios of the orders. So we can say the smallest value, minimum value of n1 is 9. So we can find the position. So y minimum will be 9 times d. So d lambda, oh right, so d lambda 1 by small d. Now d lambda 1 by small d is nothing but 7.2, so it will be 9 times 7.2. So this will be 1864, so 6.4, 64.8 millimeter is the distance where the maximas of both the wavelengths are coinciding. So in this question, in a YDSE, a double slit experiment using light of wavelength 600 nanometer, the angular width of a fringe formed on the distant screen is 0.1. So angular fringe width is nothing but lambda by d. And theta is given as 0.1. So find the spacing between the two slits. So we should write theta in radians. So I can say it will be 0.1 times pi by 180. Lambda is given as 600 nanometer. And we have to find the spacing between the two slits. So basically we have to find d. So d will be 180 times 600 times 10 raised to power minus 9 divided by pi times 0.1. So it comes out to be 0.34 into 10 raised to power minus 3 meters, or I can say it will be 0.34 millimeter. So that is the distance between the two slits. Now let us see the B part. So light of wavelength 500 angstrom propagating in air gets partially reflected from the source of water. So we have given water, and this is the interface which is separating air and water. Partially it is getting reflected and partially is getting refracted, right? How will the wavelength and the frequency of reflected and refracted light be affected? So we know that frequency doesn't change when the light enters from one medium to another, because frequency is the property of the source which is generating the wave. Now here the reflected wave is reflected in air only, right? So there will be no change in the wavelength of reflected light, but the refracted light has entered a new medium, so the speed has changed, so the wavelength will change. So for refracted ray, the lambda will change, but the frequency for both the rays will be same. Right, now let us see the next question. The ratio of the widths of two slits in Young's double slit experiment is 4:1. Evaluate the ratio of intensity at maxima and minima in the interference pattern. Now the intensity is directly proportional to the width. You can say intensity is directly proportional to the width, and we have given the ratio for the width. So I1 by I2 is nothing but 4:1. And we know what is the maximum intensity, right? It is the square of root I1 plus root I2. And similarly, the minimum intensity is square of root I1 minus root I2. Now we have to find the ratio of intensities as maxima and minima. So I max upon I minimum will be, so we can write this as root I1 by I2 plus 1 square upon root I1 by I2 minus 1 square. What I have done, I have divided numerator and denominator by I2. So this will give us, I1 by I2 is 4, so it will be 2 plus 1 square upon 2 minus 1 square, which is nothing but 9:1. Now let us see the B part. So this is the A part. So does the appearance of bright and dark fringes in the interference pattern violate in any way conservation of energy? So what happens in this, in the interference pattern, there is a redistribution of the energy. So there is a region of complete darkness, there are region of completely brightness. So there is just redistribution of the energy. The overall energy does not change. So that you should remember. And all bright fringes will be having same brightness, and all dark fringes will be dark, right? So that you should remember. In Young's double slit experiment using monochromatic light of wavelength lambda, the intensity of light at a point on the screen where path length difference is lambda is k. And find out the intensity of light at a point where the path length is lambda by 3. So with the path length, we can find the phase difference. So we know that delta x 2 pi by lambda times delta x is phase difference. Now, if the path length difference, so intensity of light at a point on the screen where path length difference is lambda. So we know that when we have integral multiple of lambda, we have constructive interference. And the intensity is given as k units. So if both the, so I'm assuming both the sources have the same intensity. Let us say I naught is the intensity of both the sources. So we can say k is nothing but 4 I naught, because we know that I max for say equal intensity sources will be 4 I naught times cos square pi by 2, and in this case phase difference will be 0. If phase difference is 0, cos 0 will be 1. So k will be equals to 4 I naught. Now find out the intensity of light at a point where path difference is lambda by 3. So we can find the path length difference is given as lambda by 3. If I multiply with k, so k delta x will be 2 pi by lambda times lambda by 3. So this is 2 pi by 3. So if we want to find the intensity, now we know the phase difference, right? This is phase difference. So let us apply the intensity formula, which is I1 plus, or you simply you can say it will be 4 I naught cos square phi by 2. So I'm going to use this formula. 4 I naught is nothing but k. So cos square pi by 3, because half of 2 pi by 3 is pi by 3. So and cos pi by 3 is 1 by 2. So this will become k by 4, right? So k by 4 is the answer of this question. Now let us the next question. So in Young's double slit experiment, the two slits 0.15 millimeter apart are illuminated by monochromatic light of wavelength 450 nanometer. So D is given, small d is given, and wavelength is given, and capital D is also given. So the screen is 1 meter away from the slits. Find the distance of the second bright fringe, dark fringe from the central maxima. So second bright fringe, the formula is n d lambda by small d, so it will be 2 times d lambda by small d, so it will be 2 times 1 times lambda is 450 into 10 raised per minus 9, d is 0.15 into 10 raised per minus 3. So I have converted all parameters in SI units. So this will be 0.01 and this will be 30. So we can write this as 60 into 10 raised per minus 9 plus 5. So it will be 6 into 10 raised per minus 3 meter. So this will be 6 millimeter. Now let us see the dark position of the second dark. So second dark will be, so the formula is 2n minus 1 times d lambda by 2d. So if I substitute n as 2, so that will be 3 d lambda by 2d. So 3 by 2 times, so d lambda by d. So d lambda by d is nothing but 3, right? So 3 millimeters, so that will be 9 by 2 millimeters. So it will be 4.5 millimeter. Now let us see the B part. How will the fringe pattern change if the screen is moved away from the slit? So beta is d lambda by small d. And if we move the slits away from the screen, then capital D will increase. As capital D increases, beta will increase. So the spacing between the fringes will increase. So beta will increase, right? Now let us see one more question. Yeah, so a beam of light consisting of two wavelengths, 650 and 520 nanometer, used in the interference pattern of Young's double slit experiment. What is the least distance from the central maxima where the bright fringe due to the both of the wavelength coincide? So we have done the similar question. So you can do this question as a homework. The distance between the slit is 2 millimeter and the distance between the plane of the slit and the screen is 120, right? Okay, now let us see the next question. In Young's double slit experiment, deduce the condition for constructive and destructive interference at the point on the screen that we've already done the derivation. Draw a graph showing the variation of intensity in the interference pattern against the position x on the screen. So basically the central maxima will be the origin, and in the upward direction we are taking as a positive x. So if we plot the intensity, it will look like this. So O is the central maxima, and all the maximas or all the bright fringes have equal intensity and all are equispaced, so that we should remember. And position x on the screen. So this is basically the path length difference, right? 2 lambda. So path length difference. So here we have minus lambda, minus 2 lambda, minus 3 lambda. But actually the distance, this distance will be, you can say beta, right? Or d lambda by small d. And this distance will be 2 beta, like this. So you should remember this pattern. Right, so now let us see another question. The ratio of the intensity at minima to the maxima in Young's double slit experiment is 9:25. Find the ratio of width. So we know that width is directly proportional to the intensity, and we have given intensity at minima and maxima. So I minimum and its ratio with I maximum is given as 9/25, and we know that I minimum is square of root I1 minus root I2, and I maximum is square of root I1 plus root I2. Right, so if we take the square root on both sides, we'll get 3/5. And from this we can say, from this we have root of I1 upon I2 minus 1 upon root I1 upon I2 plus 1. Right, so if I take root of I1 upon I2 as x, so we have 3x plus 3 equals to 5x minus 5. So 2x will be equals to 8. So x will be 4. So it means I1 by I2 will be 16. So 16:1 is the answer. So this is the ratio of the intensity, and the width are in the same ratio. So W1 by W2 will be 16:1. So the next concept is diffraction. So we're going to discuss the diffraction produced by a single slit. Now, what is diffraction? So the bending of light when it encounters obstacles which are comparable to the wavelength. When this happens, there will be a bending of light. Now let us understand diffraction, single slit diffraction, with the help of an animation. So we have a single slit and we have incident a light over it. And instead of a single spot, we are getting a bands on the screen. So it means the light is getting bent. And so light is bending. So let us see the animation. So this is the pattern. So if we show the intensity, so intensity will look like this. So at the central maxima, we have the maximum intensity, right? And if, now let's see what happens if we change the wavelength. So wavelength is increased, gap is increased, right? If we decrease the wavelength, gap decreases. Now let us see what happens if we change the distance between the screen and the slit, right? Now let us see what happens if we change the width of the slit, right? I hope it is clear. Right, so if this illustration or this animation is clear to you, let us now understand some important formulas that we have to remember, because the derivation is not in the syllabus. We have to see some important formulas. So let us say here we have a single slit, and the width of the slit, let us say, is A. So A is the width, and the distance between the screen and the slit is capital D. Now this is the first minima. This is the first minima. So we can say, if I draw a ray and this angle is theta. Now for minimas, A sine theta is given as lambda, right? Or you can say m lambda, where m can be 1, 2, 3, 4, right? Can be a natural number. So sine theta will be m lambda by A. So for first minima, sine theta will be equals to lambda by A. Similarly, for second minima, it will be 2 lambda by A, so on and so forth. Now, if we want to find the width of the central maxima, so this angle is again theta. So we can say this is the width of central maxima, let us say W. So if theta is small, we can write sine theta nearly theta, right? And if you want to find the width, then the width will be given as d times 2 theta. Now theta will be lambda by a for the first minima. So it will be 2d lambda by a. So that is the width of central maxima. And this is the condition for minimas. And for first minima, m will be 1. For second minima, m will be 2, so on and so forth. Right, so now let us see some important questions. Now let us see this illustration. So how does the angular separation between fringes in single slit diffraction experiment change when the distance of separation between the slit and the screen is doubled? So if you look at the expression, so we have seen sine theta is equals to m lambda by a, where a is the width of the slit, lambda is the wavelength, where m is an integer, and theta is the position of first minima from the slit. So angular separation does not depends upon the distance between the slit and the screen, so there will be no change. So we should remember this. For a given single slit, the diffraction pattern is obtained on the fixed screen first by using a red light and then a blue light. In which case will the central maxima in the observed diffraction pattern has a larger angular width? So angular width. So what is theta? So sine theta is given as m lambda by a. So this for the minima, right? So theta depends upon the wavelength. So if we change the light from, first we have used red and then blue. So red has higher wavelength and blue has lower wavelength. So if lambda decreases, so lambda is decreasing, so theta will decrease. So the angular width will decrease with change in the wavelength. Let us see next question. A yellow light 6000 angstrom illuminates a single slit of width 10 raised to power minus 4 meter. Calculate the distance between the two dark lines on either side of the central maxima. So we have to find this distance, where this angle is theta. Now what is sine theta? So sine theta will be lambda by a. Lambda is given as 6 into 10 raised to power minus 7 and a is 10 raised to power minus 4. So this comes out to be 6 into 10 raised to power minus 3. Right? So since theta is small, we can say sine theta can be written as theta. So it will be 6 into 10 raised to power minus 3 radians. So we have to find the distance. So let's say this distance is w. So w will be d times theta, 2 theta, right? D times 2 theta. So d is given as 1.5, 2 times 6 into 10 raised to power minus 3. So this will be 15. So this will be 18 into 10 raised to power minus 3 meters. And we can write this as 18 millimeters. So here I conclude the video on wave optics. I hope the concept which I have explained are clear to you. See you in the next video where I'll cover dual nature. Thank you.